Okay. So, good afternoon. My name is Ondřej Tic, and I study at the Faculty of Nuclear Sciences and Physical Engineering at the Department of Materials, and I carry out my research in the Institute of Physics of the Czech Republic. And I will talk about the influence of different superelastic plateau strain on fatigue life of nickel titanium wires. So at first, I will briefly remind what superelasticity is. So superelasticity is a stress-induced reversible martensite transformation from B2 austenite to the monoclinic B19 prime martensite in the case of nitinol. And you can see an example of one superelastic loop here. It is possible to obtain almost constant transformation stresses and distribution of strains in this wire is inhomogeneous. So almost 6-7% strain. The animation will work.
Is that a play?
Yes.
No.
Yes. So almost 7% strain is in the martensite part of the wire. On the other hand, only about 1% strain is in the austenite part of the wire in this plateau region. So only a ratio between austenite and martensite content is changed in this area. And the problem is that nitinol wires contain a large number of impurities, especially titanium carbide, and these particles don't exhibit superelastic behavior. So we have superelastic matrix, but inclusions, very rigid inclusions. And superelastic and also other properties can be significantly changed by heat treatment. So it is possible to modify transformation stresses, transformation strain, and also tensile strength and yield stress can be increased by precipitation hardening. And the important question is, what is the influence of heat treatment on fatigue life? And that's why we tested and compared two very different types of annealing. The first one is conventional annealing, and precipitation and also recovery processes take place in this type of annealing. The second type of annealing is pulse annealing by electric current. So it is possible to obtain stable superelastic behavior in after milliseconds of annealing by electric current, and only recovery processes without precipitation take place in this type of heat treatment. So we can separate the influence of these very different processes on superelastic behavior. And also heat treatment is necessary because cold work wires don't exhibit superelastic behavior. So now I will proceed to our fatigue experiments. So we used thin wires manufactured by Fort Wayne Metals. Cold work of these wires is approximately 35%, and also 90% cold work was used in one case. And we performed 5 very different types of annealing. So pulse heating, and also long-term aging annealing in conventional furnace to achieve a wide range of superelastic plateau strains. So after annealing, the wires were subjected to superelastic cycling at the same mean stress amplitude, and testing temperature was 20 degrees C and strain rate 1% per second. But the main difference is in the length of superelastic plateau strain. So the wire with 90% cold work exhibit the longest transformation strain, 6.7%. On the other hand, a wire annealed at low temperatures, precipitation hardened shows the shortest transformation strain. And you can also compare evolution of superelastic loop. So this is the first cycle after annealing and final cycle before failure. So I will talk about, I will describe evolution of superelastic loops during cycling, which is also called functional fatigue. So the most significant is decrease of upper plateau stress. You can clearly see the difference between the first cycle and 50th cycle. And the decrease of lower plateau strain is more than 2 times lower, which results in decrease of stress hysteresis. You can also observe an accumulation of permanent strain and also moderate shortening of transformation strain. As I mentioned, the most significant is decrease of upper plateau stress, and the decrease of lower plateau stress is less significant. However, we didn't observe any significant influence of heat treatment. So, for example, these black and blue wires, so long-term annealing and pulse heating, shows very similar decrease of upper transformation stress, about of 275 MPa, but fatigue life, as you will see later, is absolutely different. So there is no correlation between functional and structural fatigue. Here you can see evolution of transformation strain, so moderate decrease because of microstructure evolution and also residual martensite content decrease. And also accumulation of permanent strain was measured. So you can see that these wires are relatively stable. Permanent strain is always lower than 1%, but precipitation hardened wires shows slightly higher stability after the initial 50 or 100 cycles. So at first higher increase, but then more stable than pulse heated. And finally, fatigue life of the tested wires, which is the most important result of this research. So you can clearly see that the wires with longest transformation strain shows the worst fatigue life, only about 1200 cycles. On the other hand, wires with shorter transformation strain shows much better results. And I should also mention that each type of annealing was tested 5 times, and you can see scattering of each experiment. And at first we expected that dependence of fatigue life on transformation strain should be decreasing. However, such a short transformation strain was achieved by low temperature annealing below 400 degrees C, and probably internal stresses introduced by cold working didn't relax completely during annealing, which probably accelerated fatigue growth, which was also reported in the literature, and you can clearly see a difference between cold work nitinol and heat-treated one. So the difference in fatigue growth rate at the same delta K is clearly visible. And fatigue fracture surfaces and also cross-section of the wire was studied by scanning electron microscopy. So as I mentioned at the introduction, a large number of impurities was observed, especially titanium carbide, with mean size approximately below 1 micrometer. And also intermetallic phase Ti2 and I was identified. And it is important to mention that this is a combination of superelastic metrics and non-transforming impurities. So probably higher transformation stresses produce higher incompatibility between metrics and inclusions, which causes higher stress concentration in these particles. And so fatigue fracture surfaces shows very similar fractographic features. So almost no effect of heat treatment was observed. You can see two examples of annealing. So fatigue cracks always initiate on near surface impurities or defects. The final rupture is mostly created by ductile dimples, and fatigue surface area creates approximately 50 or 60% of the cross-section at the given testing conditions. And fatigue striations were also observed, but only in regions close to the final fracture, where striations should be more pronounced and with higher striation spacing. So to conclude, so aged precipitation hardened wires with shorter transformation strain shows better fatigue life in comparison with pulse heated wires with the longest transformation strain. So shorter plateau strain probably decrease in incompatibility or discrepancy between superelastic metrics and inclusions. However, aging or precipitation hardening don't inhibit the decrease of transformation stresses. So decrease of upper plateau stress was always higher than 200 MPa. So as I mentioned, no correlation between functional or structural fatigue in this. So you can see, and finally, fatigue cracks always initiate on near surface defects or inclusions, which is usual.